Hello everyone, we are Chang, Tejas, and Porijit, and we are here today to talk about our work on box embeddings as a library. Introduced by Vilnius and co-authors in 2018, probabilistic box embeddings are a novel region-based representation in which entities are represented using boxes, which is a Cartesian product of intervals and can be thought of as a trainable Venn diagram of sorts. The volume of a box can easily be calculated, and boxes are closed under intersections, in that the intersections of boxes is one again a box. Box embeddings were originally introduced to represent knowledge graphs, perform market basket style recommendation tasks, and model entailment. It has subsequently been applied to modeling joint hierarchies, such as hypernames and meronames from the WordNet graph, as well as modeling uncertain knowledge graphs, where each edge has a corresponding probability or confidence, and has also been leveraged on the output space of large language models for fine-grained entity typing. In order to implement a model using box embeddings, the first questions one encounters is exactly how to parameterize the boxes embedded in Euclidean space. Our examples during these presentations will be two-dimensional. However, boxes can be used in arbitrary dimensions. First, we observe that boxes are uniquely defined by their mean and max coordinates. The outer box here has a mean vertex of -9, -2, and a max vertex of -1 and 7. These parameters may be free or the output of some neural networks. The simplest approach to obtain mean and max coordinates is to split the parameters in half, interpreting one half as a mean and the other as a max coordinate. While straightforward to understand and implement, this does not guarantee the boxes have positive side lengths. We can enforce this using a different parameterizations, which uses half the parameters for mean and puts the other half through a soft plus function to represent the side lengths. It is also often desirable to consider boxes constrained to a bounded regions, such as unit hypercube, as it allows us to interpret their volumes probabilistically. We can accomplish this using the sigmoid functions. Regardless of the method of parameterizations, for each box, we can access their mean and max coordinates, which we put as a 2D dimensional vectors. As we observe, two-dimensional boxes require 4 parameters per entity. The representations extend naturally to higher dimensions, requiring 2 times d parameters per entity in general. Next, Tejas will take over to tell you more about the implementation details.
Hello, I'm Tejas. Our library includes support for all the main approaches for training box embeddings, which amounts to providing various volume and intersection calculations. The most straightforward of calculation is to simply take the product of the side lengths. For convenience, this is implemented as hard volume layer in our library. The default for all volume functions is actually to return log volume, which is advisable for numerical stability. However, this can be overridden with the optional log scale argument. Similarly, it is straightforward to calculate the intersection of two boxes given their min and max coordinates, and the library includes a convenience layer for this purpose as well. Lee et al. 2019 introduced a soft box variant which can be interpreted as applying a Gaussian convolution to the box indicator functions. Our library provides this as a soft volume layer, also including a temperature parameter tau, indicating the extent of softness. The volume layer is intended to be used in conjunction with the hard intersection layer and has the benefit of providing gradient signal even for disjoint boxes. Dasgupta et al. To 2020 is the current recommended method for training box embeddings as it smooths the landscape further by interpreting the min and max coordinates as random variables. Specifically, Gumbel random variables were chosen due to the fact that these Gumbel boxes are closed under intersection and their expected volume can be reasonably approximated. The library also includes support for pooling, regularization layers, as well as common utilities which are useful when working with box embeddings, for example, to create numerically stable loss functions. In addition, we also support visualization of high-dimensional boxes. For example, we can visualize two non-overlapping boxes like the graph on the left, or two overlapping boxes like one on the right. Each row represents the edge of the box projected to one dimension, with the left endpoint of a green or orange line to be the minimum coordinate of a box and the right endpoint to be the maximum coordinate of the box. And next, Purojit will talk about the demo applications.
Hello everyone, this is Purujit and today I would like to discuss results on some standard applications for box embeddings. First we have graph embeddings. As mentioned previously, boxes can be used to represent graph hierarchical structures. To demonstrate this, we trained box embeddings to represent the hypernym graph of WordNet. As shown in the figures, boxes can naturally capture such graphs where edges are modeled via containment. Given two nodes h and t, we model an edge between them via conditional probability, which uses the volume of the boxes. For example, the conditional probability of fruit given apple is 1. We train this probabilistic objective using the aforementioned numerically stable binary cross entropy laws, as well as some additional regularization. As reported in the paper, we see that our library allows one to effectively train boxes to represent graphs. We recover results in line with those previously reported, which establish that boxes are capable of capturing the transitive closure of their training data, and that regularization helps in this regard. The next task we have of natural language inference, where we are given a number of sentences and asked to predict whether one entails the other or not. For example, we have here two primary sentences and hypotheses. We pass each sentence through an encoder to get box sentences for both the premise and the hypothesis. As depicted, boxes can naturally capture the notion of entailment via containment. Once again, we consider the probabilistic interpretation provided by the boxes and trained via binary cross control. Our library provides similar results to previously bespoke models when evaluated on MNLI. In conclusion, we introduce a fully open source Python library for box embeddings. It is a modular and reusable library with extensive documentation, and we further implement proposed training methods and geometric operations in a well-tested and numerically stable fashion. Finally, to install a library, you can use pip, and here's a small example of how to use the library. And here we have a QR code to access the GitHub code base. Thank you everyone for your attention.